So good evening everyone. Uh, Yesterday we started with this Raman spectroscopy. However, due to the power cut, we could not complete it. So we will be completing this today. So uh, in our last class, what we have seen that in Raman spectroscopy, we use a laser source which emits a radiation uh, having energy which is equal to h of mu naught. Okay, so when the photons or the electromagnetic radiations over here uh, are made incident on the molecules, the molecules may scatter the photons in two ways. One is the elastic and the second one is the inelastic way. So in the elastic scattering, we have the same energy of the photon as that of the incident energy of the photon. So uh, the elastic scattering, it is also regarded as the Rayleigh scattering. Okay, so if we say that this incident photon is f mu r, then in the case of this Rayleigh scattering, we have um, h of mu 0, which is equal to h of mu r, which is the Rayleigh scattering, and this h cancels out. That means the frequency of the incident and the frequency of the scattered Rayleigh scattered photon, they are the same. In addition to that, in addition to this elastic scattering, we have inelastic scattering also. Okay, so in that case, what we have this inelastic scattering, they are regarded as the Raman scattering, and herein the energy of the photon, it is given by equals to h of mu 0 plus minus mu ra, say for example. Okay, so if you compare it with the uh, incident radiation, so what we get is that uh, the mu 0, it is either increased or decreased by a frequency Ra, which we called Raman shift. However, the Raman shift, it is given in the terms of centimeter inverse, and it is basically the wave number. Okay, so what is wave number? Wave number is nothing but equal to 1 by lambda, whereas frequency is equal to c by lambda. Okay, so if we calculate, if we find the equation or the relationship between the frequency and the wave number, it becomes frequency is equal to c into wave number. Okay, this we have discussed. We have also discussed, so if you see, if we take the Rayleigh scattering, which comes at 0 Raman shift, that means it takes the central position, and we have the Raman scattering on either side of this Rayleigh scattering. Okay, and they are having at equal positions. Say at 219 we are having a peak, at minus of 219 we will be having another peak. Okay, now the difference between these two lines, they provide information about the amount of energy retained or um, released by the photons when they are coming to the ground energy levels. Okay, so that is there. Okay, so in some cases, so if there is a decrease in the frequency, the lines, they are regarded as Raman lines or Stokes lines, and these are due to the Raman scattering. Okay, also If the frequency shift is towards a higher frequency range, that means mu 0 plus this mu RA, which is basically the shift. So if it shifts to the right hand side, then it is called anti-Stokes lines. Okay, these lines are called anti-Stokes lines. Now the anti-Stokes lines, they are having um, higher energy. Okay, so if you see the wavelength, it is reducing. When the wavelength is reducing, we have previously said, if you look over here, if the wavelength is reducing in this fashion, so from left to, as we move from left to right, that means our frequency will increase from right to left. Okay, it will increase over here in this fashion, right to left. That means sorry, decrease, it is decreasing, it is lowest, so your our frequency will be highest at this position and lowest as this position. Okay, so the frequency, it is decreasing, and frequency is related to the energy equals to h of mu. So since frequency is decreasing, so the uh, anti-Stokes lines, they are basically having higher energy. That means they are retaining the energy components as compared to the uh, this as compared to the original electrons. Okay, so this is what we have seen. See, uh, our electrons, they are at a higher uh, energy level, and when they are coming up, they are releasing the more energy. Okay, so this is the energy here. Now, we were talking about this polarizer and analyzer. So, in the polarizer and analyzer, what happens over here? uh, Sorry, we were to discuss about the schematic representation of the Raman spectroscope. So, in the Raman spectroscope, we are having a laser. Okay, then we have the collimating lens, and from this lens, what this lens does, it makes the radiation incident onto the sample, and at a 90-degree angle, uh, we put a filter to block the this primary laser wavelength. So this filter, it is basically a notch filter. Okay, this is basically a notch filter, and in this notch filter, what we do, we suppress the wavelength of the laser. The reason, because if you see over here, apart from the Raman scattering, we also have Rayleigh scattering. Okay, and Rayleigh scattering, it is having the same frequency as that of the original excitation frequency. Okay, and if you see, the intensity of the Rayleigh scattering is very high. So if you are not able to eliminate the Rayleigh scattering, then the resolution or the intensity, the values of the Raman scattering lines, they will be they will not be obtained suitably. Okay, so to eliminate the uh, laser frequency, which is basically the mu naught, we apply an optical filter, which is basically the notch filter, and this notch filter, it will stop this frequency. Okay, in mu naught. Then over there, apart from this filter, we have this dispersing this agent, which is basically the prism. Okay? Or it may also be these gratings, which will make the radiation disperse. Okay, and due to the dispersive medium, there will be decomposition of the light into its relative spectral components, and that falls into the CCD sensors, and the signal is being collected and the spectrum is being plotted. So uh, usually CCD is used over here. This is because CCD, they have high quantum efficiency. CCD has high quantum efficiency. Okay. Now, since they are having high quantum efficiency in Raman scattering, we have, if you uh, consider the what you call this sample analysis. So you are having this sample, you are uh, having an incident radiation, say h of mu naught. We are having energy of h of mu naught. Some of the sample is being transmitted. Okay, some are being absorbed, and very few of the radiations, they are scattered. Okay, now among this scattered light, the scattering, it is very few. Okay, among these scattered lines, we only have 1% of the scattering, which is resulting due to the Raman scattering. Okay, so you can understand that we are having we will be having very few amount of photons which will be generated due to the Raman effect. Okay, due to this reason, we basically use the CCD because it is having the very high quantum efficiency, which may be as high as 90%. Okay. Now, once you do this, you will be getting this kind of spectral components. So you will be having the Raman shift. So you are having this laser frequency, and accordingly you will be having the Raman shifts. Okay. Now, uh, you can have a detailed representation over here also. So herein, if you see the laser, now, there are three types of laser which are very commonly used: 532 nanometer, 785 nanometer, and 1064 nanometer lasers. They are usually used. However, in these cases, if it has been found that if the sample is a fluorescent sample, then if we use this 532 nanometer there and also the 785 nanometer, there are chances that you will be having this you will be having the fluorescence effect, and this fluorescence, so you are getting the scattering lights. Apart from this, you will be also having the fluorescence level with over here. Say if I mark it in green, the fluorescent photons. So the sensor, these are all they sense the charges, the photons, right? So they will not be able to distinguish between the Raman scattering and the fluorescent scattering. Oh yeah, fluorescence photons, not scattering, fluorescence photons. Okay, so if the sample is fluorescent in nature, then what will happen is that you will not, the detector, they will not be able to distinguish between the Raman scattering scattered photon, and the this fluorescent photon, and the fluorescence will interfere with the sample analysis. So under those conditions, usually the laser having a wavelength of 1064 nanometer, it is used in Raman scattering. Okay, if the sample is fluorescent. So this laser, it has got some problem also. What is the problem? If you see up to 800, we are having the visual this thing. Okay, so what is the color of this 800 nanometer? wavelength radiation, it is red. So beyond that, we get into the IR region, infrared region. So this 1064, it falls in the category of the infrared radiation. Now this infrared radiations, if you see, they can heat up the sample. Okay. So if there are any what you call if there are any samples which will be degraded or decomposed in the presence of the infrared, then the sample will be damaged. Okay. So this is one of the main problem if we use 1061 nanometer laser. But if the sample is fluorescent, we do not have any other option but to go for this 1061 nanometer wavelength lasers. Okay. Now, if you see nowadays, this type of this dispersive Raman spectroscopic setup, it is mostly used in the modern day Raman this thing, Raman spectroscopes. So you have the laser beams. It goes over there. Then we have a bin splitter mirror. So from here, some of the light, it goes towards the sample, and the rays are being focused onto the optics. Okay. And one of the important thing is that while laser is used, laser, if you see, laser have a small diameter. So most of the energy is being concentrated in a small area. Okay. And also the dispersion of the photons from the laser beam is less, okay, as compared to the normal LEDs, because from the LEDs the light is being emitted in all the direction, the photons are being emitted from all these direction. However, in laser beams you have a directed photon migration. Okay. So it falls onto the sample, and during this time, some of the samples, some of the radiation will be lost in the straight path. Okay. Again, as it strikes the sample, from here, the ray again moves over here. Then from here, some of the light will be rejected or sent towards the laser, and a few amount of the light will be passed through this beam splitter. It will go through this filter, which is basically the notch filter. Then from this notch filter, you'll be again collimating using a focusing optics, so that it focuses the light onto this entrance slit. So so this radiations over here, it passes through a very small entrance slit. It is usually in the range of 0.1 nanometer. Okay. And so it may vary up to 1 nanometer also. Then from here it goes into the this is a mirror. So this mirror reflects the light over here onto the grating, and then this grating, it decomposes the light, and that decomposed light, it is being focused onto the CCD sensor. Okay. That focus, this decomposed light, it is focused onto the CCD sensor, and then you can get the spectra in a computer. Okay. Now, what are the advantages of Raman spectroscopy? The water molecules, they strongly absorb IR, okay, but they have a weak Raman scatter. Okay. So due to this reason, we will look into the IR spectroscopy. Since water molecules can absorb a lot of IR radiation, so what happens is that if you make a solution of some analyte in water, and then you want to do the IR, then what happens is that you will be having peaks which are mostly due to the this water peak, okay, water absorption peak. the peaks of the samples, they will be very small, and you will not be able to resolve the peaks properly. Okay, so if you look into our biological system, in our biological system we have almost 70 to 80% of water in most of the cells, tissues, and whatever the proteins you say. Okay, so under those conditions, since water is present, you will not be able to use IR for the analysis. In such a case, the Raman's scattering or the Raman spectroscopy, it can help in the analysis of the biological samples. Okay, as for example, we can go for the analysis of the myoglobins. Okay, since water has very low or very weak Raman scattering, water is regarded as a good solvent for many of the Raman for the analytes if you want to do the Raman spectroscopy. Okay, because most of the analytes which we use in our day-to-day activities, they are mostly soluble in water, especially all the biological samples, and hence uh, the Raman spectroscopy, it plays an important role over there. Okay. Then in IR spectroscope, we have to use specialized um, this sodium chloride or mm, sodium bromide or sodium iodide optics. Okay, usually sodium chloride optics are used because it is quite easily available. So these optics are used for making the IR spectroscope scope elements. Okay, however, as you all know, if you keep sodium chloride, your table salt, in a container open, then especially during the rainy season, you will find the sodium chloride, it will absorb a lot of water. So it is hygroscopic in nature. So when you are working with IR spectroscope, you have to be very careful that this sodium you have to save these optics uh, in a proper way, otherwise the spectroscope will be damaged. So a lot of care is needed for managing the spectroscope. Okay, on the contrary, the convention in Raman spectroscopy, we can use the conventional optics which are made up of normal glasses, because the radiations which will be generated, it will be in the visible range. Okay, then as I said, samples having diameter as small as 0.1 nanometer can be analyzed using uh, the one spectrophotometer. Okay, then we can also analyze colored samples. So in IR radiation, what happens? Some of the samples, if they are colored, they may absorb the IR radiations and they may heat up the samples. So which may destroy the sample. However, in Raman spectroscopy, uh, it is not the case. We can use the colored samples also. Okay, but there is some limitations. Then all three types of samples, gas, solid, liquid, whatever the sample may be, we can analyze any of these samples, and that too without any sample preparation. Okay, in any of the spectroscopic methods, the sample preparation is one of the important technique, and since you do not need to prepare the sample before you do the analysis, uh, the Raman spectroscopy, it is considered to be a better or the user friendly spectroscopic method. Okay, whatever the sample you want to prepare, you can prepare those samples and you can just take it um, to the machine, and you just load it to the machine and your analysis will be done. Okay. There are certain disadvantages also. Okay. So what are the disadvantages? The sample decomposition. As I said that some colored samples, they may be absorbing infrared radiation. So if you use this 1061 nanometer laser, which is in the IR radiation, then it may absorb the IR radiation, and it will result in the decomposition of the samples. However, there is a way around over here. Usually, if it is a solid or sample, then the solid is being converted into pellets. Now, these pellets are put into a holder. Suppose this is the holder. Now, this holder, it will rotate the sample. Okay, it will rotate the sample. So due to the rotation, whenever the radiation falls from the top, it will not fall uh, on a fixed place. So during the rotation, at every time it will be the rays will be falling onto a separate region. So in this way, we can reduce the heat generated or the heat absorbed by the samples. Okay. So this can help you in preventing the sample decomposition. And again, as I told you, some of the samples, they may be fluorescent in nature. So the sample's fluorescence, it may interfere with the Raman scattering. Okay. So these are some of the advantages and the disadvantages of Raman scattering. Application. So you can go look into the compound distribution within a sample. Okay. So if you have a sample, say like this, you can do the scanning um, at a particular location. Then after this area, you can go for the scanning at a next position. Then after that, at a next position. In this fashion, you can go from left to right. And again, as you are done in the first row, then you can start the scanning in the second row. Okay. So this is called raster scanning. So that will help you in understanding the compound distribution within your samples. Okay. Then you can look for the blend uniformity. Okay. From the intensity of your Raman scatters. Okay. Then you can go for high throughput screening. Okay. Then we can go for the powder content and the purity of some of the samples. We can go for that. Then raw material verification. It is a qualitative method. Okay. So over here you can find out, as I told you before, that this the lines which are being formed, they are specific to a molecule. So at what position you are getting the peaks, from there you can have an understanding about the whether the material is the same material what is being proposed or it is a different material. Okay. Then polymorphic forms you can detect, even though the what do you call say fat. So even though the fat is same, so if you cool the fat at a lower temperature, it will be crystallizing in a different form. If you cool it at a slow rate, the fat will be crystallizing in a different polymorphic form. So you can find out that one. Then you can try to find out the changes in the crystallinity. Then if there is any contaminant, you can identify those. Again, you can find do this using the qualitative analysis method. Then you can go for the combinational chemistry. Then in vivo analysis and skin depth profiling you can do. Then doses contain uniformity in the pharmaceutical formulations. Then you can also analyze the single walled carbon nanotubes. So what is the purity of those right? Then what are the electrical properties of the carbon nanotubes? You can predict it from the Raman scatterings. Okay. So diamond like coating properties, so we call it DLC. So you can look for those. So if there are any defect or disorder within the carbon materials, you can try to find out these things. Then diamond quality and provenance. So what is the quality of the diamond? You can find out this thing. And the electrical properties and number of layers of graphene based systems, you can find out those things. Okay. So these are some of the applications of Raman spectroscope. Now, this is over here you have the spectrum of TiO2, the difference between rutile blue and anatase red phase over here. So if you see the rutile, it is basically polycrystalline in nature. From here, if you see all of these peaks, they are having different thing. So whereas in the anatase phase, if you see, there is only one major peak. Okay, so it is what do you call it? It is more towards a monocrystalline phase. This anatase this thing. These peaks are also there, but in the anatase phase, these peaks they are quite small. Okay. Then, if you are having polycrystalline, that means crystalline plus amorphous regions. If you have that kind of thing, then you will get a broad peak like this. And if it is a monocrystalline peak, so you will get a sharp peak like this. Okay, so from here you can say, if you see this is a monocrystalline peak. So here, if you see, there are multiple crystalline peaks, right, in the rutile phase, okay, of the TiO2. Whereas in the anatase phase, you are having over here also you are having, but most of the peaks are at this position, at this sharp peak. So it is near, it is also a polycrystalline phase, but one of the phases it is more prominent as compared to the other phases. Okay. So the homogeneity, the properties of the sample, wherever you try to pick up, it will be similar at all the places. Okay, whereas over here the homogeneous property may not be present. Okay. Now then we go for this hyperspectral Raman imaging. What happens is that nowadays we have Raman microscopes. So you have a microscope peak arrangement, and then you have the samples over here. So I was telling you about the raster scanning. So it basically does this thing. So what you do, you have the sample like this. Then this objective of the microscope through which there is a specific arrangement over there. So the light falls onto through this objective onto the sample, and then again it moves into the optics of the system. So what it does, it looks into the sample as it is a it is having some array of area, small arrays. So first what it will do, it will come at this position, it will scan, it will record the Raman spectra, and if you have the information what phase it is, it will record the information over there. Then it will go to the next position, it will again do the imaging. So first it will complete the first row, then it will complete the second row scanning, third row scanning. So in this way, it will go and it will find out what are the phases or the polymorphs which are present, and accordingly it will give you a color coded regions. Okay, so that is called hyperspectral Raman imaging. So, so for each of these, it will calculate the Raman spectra. Are you getting my point? For each of these, it will calculate the Raman spectra. Okay, and from the Raman spectra, it will automatically calculate by applying the artificial intelligence. It will calculate, or machine learning method. It will calculate what phase or what type of material it is, and it will then just give you the images like this. Okay, so hence it is called hyperspectral. Okay, so hyperspectral Raman imaging, that means at each of these location it is calculating the spectra. Okay, it is calculating the spectra in a very small portion, and then it is identifying, and then it is telling you uh, what type of material you are having at that position, and accordingly it is doing the stuff. Okay, so this is it for the this Raman scattering. If you have any questions.
Sir, how we will be using this Raman spectroscopy in API concentration?
I told you na. Yesterday only I told you. So suppose uh, you have these peaks. Okay, so the intensity of this peak. So usually what happens is that you take the Stokes sides this thing. Okay, so what happens over here is that you have this one, the intensity of these things will vary. So suppose if I draw a simple this thing, you have a you have the Rayleigh scattering line, then you have a Stokes line, you have anti-Stokes line. Okay, so the depending upon the sample what you are analyzing, this Stokes line, suppose it will appear at a particular wave number. Okay, and once you've identified that suppose you are talking about say aspirin, you want to identify the quantity of aspirin in a particular what do you call, in a particular this thing, what do you call, in a particular formulation. Okay, so first we will be identifying at what position our this aspirin it gives the Raman scattering, or we get the Stokes line. Okay, once you have found out that thing, then you have to make a standard curve, concentration versus intensity using a known sample. So you will be getting something like this. Then when we will be analyzing the unknown, you will be getting some intensity over here. Now from here you calculate, you just put the value of intensity. From here you will be getting y equals to mx. Last time we have talked about. Okay, now from here you have the m, you have from the test run you will get the y intensity. Okay, so you find out x, which is the concentration, right? So all the quantitative analysis what we do using the Raman spectroscopy, they are to be done in this fashion. Okay, so you have to find out a standard curve, because under a specific environment you don't know how it will behave. Say for example, you are using water. Today you have made the water using your water distillation apparatus, but tomorrow when you are making, due to some reason, someone has used it incorrectly. Maybe some contaminant or impurity it has come into the water. Okay, or there is some changes in the internal, or even when you are getting the solvents, there might be a batch to batch variation. Okay, so even when you are using solvents, there might be some minute changes, which we call batch to batch variation. There will might be some batch to batch variation, that according to that also there might be some changes in the absorption and the scattering profiles. So while you are doing this quantitative analysis, we need to make the standard curve, and once you have made the standard curve, then you go for the analysis. Okay. So anything else?
When these radiation are passing to the slit, they are falling on this mirror. So they will be losing some energy or not?
Where?
When these radiation are falling on the mirror,
Uh-huh.
then they will be losing some energy in a sense.
No, 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 no. if you remember correctly, during our UV spectrophotometric analysis, we said that when you are using this mirror, these mirrors they are aluminized at the front. So glass may have absorbed something, but since you are aluminizing the glass on the top, so it is reflecting all the things. Okay. Yeah, another important thing which I forgot to mention, this polarizer analyzer. In some of the cases, you will find after this thing, you may have a polarizer over here and polarizer just before the filter and all this thing, this analyzer. So this is your polarizing sheet. This is another polarizing sheet. Okay. So you must have seen that if you have two polarizers and they are overlapping, and if you want to see through this, and if you rotate one of this at one position, at one point you will be getting that all the light is being transmitted, and at some position you may have some other lights are being all the lights are being blocked as you rotate it, right? So using this you may go for the analysis of the some of the samples which may which may have some effect on the analysis. So those kind this setup, this polarizing and analyzer setup, this is the polarizer. This first, front one before the sample, it is called polarizer, and the next one it is called the analyzer. So this polarizer analyzer setup, it helps in understanding the symmetries of the molecular vibrations. Okay, I'm not going into the details of this one. Just I would like to know that using this polarizer analyzer set, you can go for the symmetric vibration analysis of the symmetric vibrations, molecular vibrations. Okay. Yeah, please tell me anything else. I hope I have answered your this mirror question. Anything else? No?
No, sir.
Okay.